I have an example, and similar to the CPU model, we also have a FPGA-based toolbox. So I can go back into the add-on manager. We'll see I have this HDL Coder Support package for NI FPGA hardware. I can open up documentation just like the CPU toolbox natively within the application. And we actually ship an example. In this case, we can walk through all these commands. It's a simple half-wave rectifier model. It's a Simscape model as well, so we support that environment. And I'll step through a little bit what that model is and how we can actually compile a bit file compatible with NI FPGA hardware now. So to get started, I'll open up that model, which should be, let me open up my half-wave rectifier. So as I described, it's using Simscape, so physical components. Basically has a resistor and a diode. We have a single import that's a voltage input and 3 outputs measured. By default in the simulation here, we're providing a sine wave that's here with an amplitude of 10. And I also have a scope in my model to visualize the expected output. So just to demonstrate what this output should represent, I'm going to open up my scope and run the simulation. And we can kind of see it's a half-wave rectifier, so it's only really capturing half of that input voltage, that waveform. We can also measure the voltage through the diode here as well. What we would expect is when I bring this onto FPGA is that we get similar response. Like ideally, anytime we're simulating something in models, we want that same response to be reflected when we're actually bringing that model and running it in our RT target or on the FPGA. Otherwise, like the simulation just won't be representative, and that's what we really want to show when we're interfacing with a physical DUT. So now that I have this model, how do I actually get it onto the FPGA? How do I compile a bit file? Well, first thing I can do is run through and generate my implementation model for my Simscape model here. So I can go back into my example briefly. And I can bring up the Simscape HDL Workflow Advisor. I've run through this beforehand, but just wanted to demonstrate that I can set my different solver configurations. I can set my target frequency and generate an implementation model. One thing to note here frequently for users is a challenge to take maybe a model you've just have in simulation mode that uses doubles, which is the default, and how do I actually get that on the FPGA when doubles aren't supported? Well, the easiest way is just to be able to translate everything into single point precision. Floating point is possible, but you're at risk of maybe losing some fidelity. It's also more time consuming to translate everything. So with NI's HDL Coder toolbox, we're actually supporting single data types to facilitate this. I've already gone through and generated that implementation model that I can pull up here. And what we see is a lot of it looks similar on the outside, except now I have this HDL compatible implementation model. By default, I've also added an extra import that I'll touch on. But what I can do from here now is enter in the workflow advisor, which is kind of the getting started point for generating any VHDL code from a Simulink model. And what NI's done has implemented a target workflow natively into this window and workflow that supports NI FPGA bit file generation. So I will select that workflow. From here, I can select my target platform. In this system, I have a 7868R installed on the system. That's where I want my model to actually be deployed. I'm going to run this task, which will start kind of generating the project that will require to actually compile out this bit file. From here, we don't offer any existing other reference designs. I'll touch on this later as something we're looking to open up to users, but for now, we kind of just ship one out of the box that handles everything for our customers. Once that generates, this is where it gets a bit more interesting. We have our target interface. So I have 5 ports in my model, as I mentioned. We have our 1 import, I have 3 outputs, and I have that 1 duplicate. The reason why I created a duplicate today is we have a couple of platform interfaces that we can connect these ports to. For the most part, I'm just connecting to registers, which means I'm taking those ports in our FPGA code and bringing them up to our CPU level to interface with on the RT target. However, in some cases, I might just want very rapid response, measurement or output directly on the FPGA on a physical line. In this case, I've taken this physical output port and connected to a physical analog output on my 7868. I can run this target interface, and that's going to start making those connections behind the scenes for us. Once that's generated, I need to select my desired model clock frequency. The example goes into this in a little bit in the documentation on how we might calculate it based on the actual solver time of my model, as well as my number of iterations to actually solve this equation. In this case, I'm going to use a model clock frequency of 180 megahertz. Can run this task again. And this is the first time where you're starting to see LabVIEW populate in the background. So traditionally, we've forced users to kind of have to manually do this all in LabVIEW. What this toolbox really accomplishes is allow myself to stay within Simulink where I'm comfortable and not have to interface with a programming language that I'm not as familiar with. The next two steps I'm going to breeze over a little bit. They're kind of just common in most of these workflows. There's nothing particularly special about NI's impact on this workflow. I don't really need to make any modifications out of the box. If I wanted to, I could make some edits directly for the HDL code generation settings, but in this case, I'm already content with the default settings here. And once this completes, the last step is really going to be about creating and compiling my project. So as I mentioned, now we can actually generate a LabVIEW FPGA project and compile a bit file. I have options to select my compile server between doing a local compilation or perhaps even on the cloud, either kind of one designed by our customers at their sites or using NI's LabVIEW FPGA compile cloud server. I can select specific Xilinx compile options if I want to, say, benefit or really focus on speed or saving size. I can then actually generate a standalone LabVIEW FPGA project if I had a desire to edit any of the code there or add additional LabVIEW FPGA functionality. For some of our users, though, we just want to compile the project. So I'm going to kick this off. So what it's going to be doing behind the scenes now is actually scripting out that LabVIEW FPGA project that I mentioned. And once that is complete, we will begin the compilation process for a bit file that we'll eventually bring into VeriStand and deploy. So right now, we've kicked off an external window. I could have this all compiling within MATLAB. What this allows me to do is maybe I want to compile this in the background and continue using MATLAB or even close out of the environment. Compilation of bit files can take some time. For a simple model like this, potentially even half an hour. More complicated models, a couple hours. Luckily for this demo, I've kind of done this beforehand. I can show some of the output here. It's expected once we kind of get through this initialization stage, we actually output our estimated device utilization, the timing, as well as what actually occurs. And then we can see I have my bit file path generated. I've already done this ahead of time, so now I'll bring this over into VeriStand. So back in the VeriStand environment, I'm going to switch over to a project I have pre-created for demonstrating how to bring in a model here. So I have a screen. What I can do is go into System Explorer to configure my system definition. And once I have that up, how we interface with this bit file in VeriStand is through our FPGA add-on custom device. It's as simple as just specifying my bit file path. In this case, if this is my bit file, my HDL subsystem, and I have all my scalars, so my inputs, into VeriStand, which are really going to be my outputs here. So I have my 3 as well as my additional output that's going to be created for any of these models. My outputs, I have my voltage input as well as a clock enable signal that will actually trigger when my model starts here. The reason why I selected that one analog output in my model is that it's actually going to be looped back into a DAC analog input just so we can test in this case and show that, yes, I actually am receiving that signal physically. In the real world, I'd be sending that signal out into my DUT itself. So similarly to the engine demo, I can now deploy this down to my target and get ready to see responses on my screen. And now we are actually seeing responses. So right now it's kind of just like the analog input seeing a very little bit of signal. I mean, that's within the range of noise for this device. So I mentioned I can click on my clock enable. Right now I'm not supplying any voltage into my model. manual, I can just apply maybe a static value, and we'll start seeing some response. Now, what'll be more interesting is in the response we saw in Simulink, I was supplying a sine wave of amplitude 10. In preparation for this, I created an RT sequence that'll deploy down to my target and set values similarly with a sine wave of voltage 10. So what I'll do here is actually start this, which will compile and deploy that file down to the target. So right now it's compiling, deploying, and pretty quickly we'll start seeing some very fast responses. It's a little bit overloading the screen here, but what I can do is pause that, and let's zoom in on the response here quite a bit. And what we can pretty quickly see is this mirrors a lot of what we were actually seeing in Simulink. So I can see this is my sine wave voltage input. I can actually then receive kind of these current values, which matches kind of what we'd expect from our Simulink response. In addition, as I mentioned, I had that loop back for one of these here that I'm measuring back with my DAC analog input channel. That's exactly mirroring the signal that I'm getting back into my CPU, which is a great sign just to show that my physical output's mirroring that. And then lastly, we can look at my diode voltage. That matches also what we were seeing in simulation. So overall, this is a fairly straightforward process of I could stay within Simulink and generate an output bit file, bring it over into VeriStand, import with a few clicks, and be able to deploy. Similarly, if I just wanted to automate this all, our Simulink toolboxes are all abiding by the MathWorks' API, so I could script a lot of this functionality. In addition, for the FPGA add-on and VeriStand as a whole, I can script this functionality. An FPGA add-on, there's some documentation available for how I could actually script this automatically. So say upon a new bit file created, I want to just automatically trigger, import that into my VeriStand system definition file, and deploy without necessarily needing to go through these manual steps.